Today we are going to do section 3.4 on page 298, partial fractions. Now the principle of partial fractions is very straightforward. The only problem is actually doing it. It's a lot of grunt work. Now let me show you what I mean. For example, if you were to integrate something like the integral of 1 over x plus 1 dx, the answer is very straightforward. That's just a natural log, okay, which is of x plus 1 plus c. So that is the principle that we're gonna go by. So then how do you integrate something like this? As your book shows, some random fraction, rational polynomial, is not a polynomial, but rational fraction that I'm looking at, minus x minus 2, let's say. Now, how do you integrate that? That is, nothing look like this. But there is a trick in algebra that you can, if this thing can be decomposed into things that look like that. In this case, it equals this thing. If you break this thing apart, it becomes something like 1 over x plus 1 plus 2 over x minus 2. What happened is that you factor out the bottom, becomes these two things, and then arrange it such that, when you do the common denominator, this shows up. You might remember that you've already done this in algebra, or maybe pre-calculus, I don't know. But if you don't remember how to do that, there is the way to do it is fairly straightforward and quite annoying. Okay, I mean, it's even more annoying than doing the common denominator, which you've done many times, right? But to break it apart is even worse. So it takes time. So please, if you don't remember how to do it, please look at the book's explanation. Where's the explanation? Well, somewhere, a couple pages later. But as to how to do it, it's quite straightforward. But more importantly, you should try to figure out how would you do that exactly. If you can't remember how to do it, how would you figure it out? What kind of stuff would you put here in order to make this thing, to reverse engineer the common denominator thing that you used, that we normally do. So but I'm not going to go in detail for that, okay? Because I'm not doing that because this is a ton of grunt work and I do not like grunt work. So what I'm going to do is in the description under this video, I have something called partial fractions calculator. Now, nowadays, life is sweet. Back in the day, we have to do this junk by hand. But now there's something fancy called partial fractions calculator, which means that you type this thing in and this thing pops out. That's how neat it is. Now, this process isn't always possible. For example, what if you can't factor this? This thing has no root, then this is not going to happen. But even then, when that happens, then we have to pull a different trick that I'll mention later. But for now, it's just when you see a fraction, the trick is to break it into some kind of a thing like this, if possible. So to explain it, let's look at example 3.28. Now, what's that? That is in a case where you have a power on top that's more than the power on the bottom. This one is less, okay? What happens when the power is more? Then your answer, you're breaking stuff apart, will end up with some kind of maybe some kind of x. It doesn't make any difference. How do you do that? Well, you do something good old thing that you've done since 5th grade. And then there's an upgraded version when you did algebra. It's called long division. Again, if you don't remember how to do long division, there's no shame in that. Just look it up, how to do long division with polynomials. Long division is a lot easier to do than breaking stuff up blindly. Okay, you have to figure out two things, what these things are. Whereas long division is a lot more pleasant. However, let's just use that. For me, I just use the partial fractions calculator. And yeah. And you type that in, and then you'll do long division too, that part of it, so that everything falls apart. Well, I don't think I even tried that kind of problem yet. Doesn't matter. The point is that's how you do that one. So please do example 3.28 as your homework. It would be very good for you to practice long division. Actually, I don't know if that's true, but let's just say it is. So next, let's look at the next thing, partial fractions with something. Whatever. Let me see. So example 3.29, the next example, give you now the fraction is becoming slightly more complicated, x to the power 3, etc. on the bottom. At that point, nothing changes for our calculator. Although I didn't try this problem on the calculator, I assume they can pull it off just fine because the process is only tedious. There's nothing hard about it. So please figure out how to do that. I mean, preferably figure out yourself without looking at the rules. But do look at the rules because they have a two method of figuring out what these things are, which is extremely tedious to me. So I'm just going to type it into the fraction calculator that I showed you. So once you take that thing apart, then the answer will be very straightforward. Yeah. And then you can, well, come up with it easily. But the hard part, of course, is taking the whole thing apart. Now, please be sure to do the examples as homework, the ones I assigned, because the reason I assign them as homework is because it's much faster for you to do them yourself than to watch me do it. It'll take me forever. And you will learn nothing because these things are all tedious and straightforward. So example 3.30, we have, so please do example 3.29, and let's go to example 3.30. The division by applying partial fractions. Nothing interesting happens here, really, that I notice. You just use the partial fraction calculator, break that thing apart, and then come up with a bunch of answers right away. That's all involves the natural log. So that's that. Now, of course, you can say that if you were to take some exam in school, then you probably won't be allowed to use the partial fractions calculator. And that's why I say that you should know how to break this stuff apart. But once you know how, let's not bother doing any more than we have to. Okay, let's not lift a finger more than I have to. That's the way I live. Anyway, so example 3.30, please also do that one as homework. It doesn't seem to be particularly difficult. However, just because it's not difficult doesn't mean it isn't extremely tedious and might take you forever. But that's the way it is. Sometimes in calculus, we have to put up with some tediousness. Okay, that's part of the charm. Well, it's not going to be tedious all the time. Especially you have the partial fractions calculator, which removes a lot of the tediousness something about it. So let's look at the next example, 3.31. That is similar, but now we're looking at some trigonometric situation. Well, in this case, being that the derivative of the bottom sine, there's a bunch of sines on the bottom, and then there's a nice convenient cosine on top. So we're going to do a basic substitution of u equal to sine of x. That will end you up with some kind of a polynomial on the bottom. So we will use our newly learned skill of breaking that polynomial into simple fractions so that we can apply the natural log. So please do example 3.31. Next, let's look at example 3.32. Now we have an integration that has an unusual situation. That is, there's a squared to the bottom. They already factored this for you. And so you can save some factoring, but that doesn't really make it much better because this thing is going to be, what happens when you have something that has a squared? That is, the factor showed up twice. Well, what end up happening is, if you investigate what happens in this kind of situation when you do the common denominator, is that the original thing has to come up twice. That is, if you look at a different page, is it decomposes into something like the factor 2x minus 1 has to appear by itself, and then it has to appear again as a squared version. I'm talking about well, anyway, so I'm talking about this. See the ABC on the top of the page? Yeah, see, A is over 2x minus 1. Then you have to come up with another B that's over 2x minus 1 squared. and then you come up the last number C, and so the whole thing come out, which means this is even more tedious than before. However, I will use a trusted fraction calculator. If you can't find one, then if that link isn't available anymore, or when you watch this video, or you just can't find one, then I guess you just have to do this. There's a time to do dirty work, and the time might be right now. So, but anyway, and once you grind through all the work of breaking the fraction apart, then you can come up with the answer, and the answer again is fairly straightforward. So the hard part here is just doing basic. This is not basic, I guess. Doing algebra, okay? Basic or not, it's just algebra. So that's that. So please do this example 3.32, as part of your homework. Next, let's look at example 3.33, a couple pages later, where we are evaluating something that has yet another twist. What happens is it has something on the bottom that cannot be factored. Okay, like I mentioned earlier, what if you cannot factor the denominator, or at least part of it? So in this case, then the factor only goes down one step. You still are left with something like this one. And what you do in that case is then you will make up the numerator will need an x in it. Okay, so then you have to decompose this thing into A, B, and C, where A, B, and C are numbers. Or you can use the factor calculator that I showed you, and just type it in, all the answer come out. You don't have to get your hands dirty. Your choice. But you should probably know how to do this though. So please do this like one time, okay? And once you've done it one time, then that should be good enough. But I'm not going to do it one time because I did this before, I think. Anyway, so once you take that thing apart, do enough algebra, tedious algebra, until you break that thing apart, then the integration comes fairly readily. Now, in this case, I want to point out that for the integration, once your fraction got broken apart, so you can integrate it. Now, the first term is 3 over integral of x over x plus x squared plus 1. That's a convenient use substitution. Now, look at the second integral. It's just 1 over x squared plus 1. How do you integrate that? That might not be that obvious, but in reality, however, what you do is pull out the integration charts. This is back from Calculus 1, where you notice that in the middle here, on this side, where the integral of 1 over 1 plus x squared is tangent inverse. Okay, the tangent inverse of x equal to all that stuff. That was proven back in Calculus 1, so we're not going to reprove it. We're just going to accept that and then plug in here that information. As you can see, that's where that's where the book got that information, is that 1 over x squared plus 1 is just tangent inverse x. And after that, that would be, then your answer comes out right away. We'll talk more about how to use all the charts later in the next section or something. So for now, let's move on. But before that, make sure you do example 3.33 as your homework. Next, let's look at example 3.34. This is on page, we are still on page 305, where we're going to integrate yet another fraction. Now, this fraction has a slightly different twist, where you have to calculate something that has an irreducible factor on the bottom. So once you factor out that thing, your problem doesn't look that hard. X cubed minus 8, 1 over x cubed minus 8 that you're integrating. But once you break it apart, it actually looks a lot worse. So now you have breaking it apart. You have I will show you here what I'm talking about. Looking down a little bit down, where right here in this row, where you have the integral equals to 1 over x minus 2, which is an easy thing. But then the other one is x plus 4 over that quadratic thing, which is much harder. Now, how would you do that? There is no tangent formula to handle that one directly. But here's where you pull a trick. Is what you do is called completing the square. which is done, yeah, which is also done before. But if you don't remember how to complete the square, it is very straightforward. What happens is that, let's say you have this particular thing, okay, x squared plus 2x plus 4. Now, and what happens is, now in this case, this number is just 1. If it's not 1, then you have to factor it out to make it 1, and then complete the square on the inside. So it will just have a number stuck on the outside attached. But so let's say this number is 1. What you do is that you write down to complete the square, you write down the first term, and then you write down the second term, and then you divide by second term by half, okay, and then square it. So half of 2 is 1, and then you square it again is also 1. So half and square, okay? Then you add 1 to it. Then why am I adding 1 suddenly? Well, you subtract it later to be fair, okay? So then this is what you have. That's the completed square. And then then you write down the rest of it. Plus 4 minus 1. Now this equation is the same. I mean, this expression is identical to this one, because I added 1 but then subtracted 1. See? So I'm being perfectly reasonable. And then, so then your completed square becomes x plus 1 squared. And then you do the math here, that becomes plus 3. That is called your completed square, which is what your book has. Okay, so now why are we doing this? We're doing this because we're turning this thing into another use substitution with the tangent inverse. Okay, remember what is the tangent? The integral of 1 plus x squared, as I showed you a little bit before. See the middle one on the other side? Integral of 1 plus x squared is tangent inverse of x. Now, so we are going to take this whole thing as u. Then it becomes identical to that situation. Whereas this one is that's not a 1, but we'll fix that. Okay, that's just a numeric. You just adjust that number or something. So now we have. Let's look at the next page to see how that is done. To integrate that, we have. Well, in this case, we don't even have to do that much. What we're gonna do, okay, so we're gonna let u equals to x plus 1 right here, and then we'll attack only that part of the integration. Okay, look at the top of the page where we have this thing going on. We have x plus 4 over all those things. What you do is you substitute u as x plus 1 on top here, and once you did that, then you break it apart. Okay, now you're going to break it apart into 2 fractions. And then the first fraction, which has a u on top, we'll use a direct substitution. The second fraction has no u, but it's a squared plus situation. So you're going to apply that tangent rule that I showed you. Whereas, yeah, and then, but you have to adjust it a little bit. So the actual formula is 3 over, actually, let me just show you the actual formula. Okay, I got it. This is Appendix A in your book, at the end of the book, that is. And when you look at the Appendix A, Rule 16, look at number 16. The integral of a squared plus u squared is equal to 1 over a tangent inverse u over a. That is, if a is not 1, then you adjust it by dividing it in 2 spots, okay, in front and within u. And that will make everything work out. So that's how we came up with that. And and as a result, in this case, a is equal to square root of 3 because you're integrating u squared plus 3. Okay, so you fit that into the formula and everything will come out nicely. And let's see, what else do we want to do? Oh, that's not all. Okay, once we did this, we have to, that's just part of the answer, right? We have to remember the rest of it. And so then your entire answer, when you rounded up the first part and the second part and all the parts, then you get, well, you get some. Then eventually you end up with this. When you look at the bottom answer, that is one long answer. You have not done that many problems with such long answers, but we need to start getting used to that. Okay, some of the answers are going to be quite long. even if the problem is fairly short, but that's okay. You just patiently go through one after the other until the whole thing is done. So please make sure you redo, what example is this? Yeah, example 3.34 as part of your homework. So we have come to the end of the section, and so we are going to do some homework next. Please notice that at this point of mathematical studies, you might notice that I don't talk about a lot of the details. That is, you're not going to be held by the hand and spoon-fed every step of the way. By Calculus 2, you are expected to take a lot of initiative yourself, figure out how to do something, and look it up if you don't remember. And get through all the details, because that is really the only way to learn advanced math. Because as math gets higher up, it might take longer and longer to do something, and it's not possible for the professor to go through each problem and every single detail. It just doesn't make any sense. But if you do it yourself and patiently and then build your own path, then you can learn calculus, get a good solid grasp of calculus, and not like that other guy who just sat through class and barely know a thing and didn't understand a thing when he's out of the class. Okay, so please do the homework for today, which is page 308. Section 3.4 problems number 197, 201, 205, 209, 213, 15, 19, 21, 27, 29, and 43. And I have a hint for 243 in case you look at it and have no clue how it's done. But the hint is on the bottom. So, well, just below. So, but anytime you have a hint, first try to do the problem without looking at the hint. And if that doesn't work and you're getting nowhere, then it's time to look at the hint. So please do your homework. And when you get back, I will talk about the homework. Now that you have finished the homework, let's talk about some of them. Problem 197, quick and easy one. You have a simple problem that well, it might be simple now, but it was impossible to do just a section ago, right? Without knowing the partial fractions trick, you couldn't begin to do this problem. But we do know the partial fractions trick, so we're good. So 197, you break the fraction apart into two chunks by I did it with a fraction calculator, as you can see, because I didn't spend a drop of sweat on it. And then the whole thing just come out as the natural log of those the denominators. So that worked out nicely, and that is correct. Next, let's look at the next problem, 201. That one looks slightly more complicated, and as you can expect, the next thing you know, there's something on the bottom that cannot be factored. So what do you do when you can't factor it? You pull the stunt called the completing the square. Well, if you don't remember how to do completing the square, that can be easily researched online. It's a very straightforward process. Well, I did an example here. So once you do the completing the square, then you have that square situation. So you have this, and then you let u equal to x plus 1, right? And then plug the u in there, so that thing becomes a u situation, and apply the tangent inverse formula, which is right here. I copied the whole formula here from the book. So the integral of u squared plus a squared is straightforward tangent inverse with a bunch of a's dividing to adjust for a if a is not 1. And so then the answer comes out right away. Yeah, let's see. And then don't forget the plus 2x. That's from the previous part, because right, because there's a 2 here, right, in your partial fractions. So then there's a plus 2x at the bottom. And so don't forget it. Just because it was easy to do, sometimes you just tackle the difficult part and then forget your part of the easy answer. The easy part of your answer. Okay, next, problem 205. Same thing. We have the x to the power cubed, which would have made a very difficult, well, maybe not very difficult, but very tedious process of breaking the fraction apart. So I used the fraction calculator, which very conveniently spit the answer out at me without having to lift a finger right here. And as a result, then the integration is completely straightforward right here. And then the answer is correct. When I say the answer is correct, that means it is identical to the back of the book. And then let's see, the next problem, the same thing. Yeah, 209, even more straightforward, it seems. You have, is that the question? I guess that must be the question. Or maybe I didn't even write down the question. I don't care. The point is, you see, the answer comes out in 2 lines. I probably didn't even write down the question, just wrote down how the fractions split up. But that's good enough. Okay, so let's move on. The next problem, 213. All right. Okay, next problem, problem 213. We have, and now we have a situation where part of the denominator cannot be taken apart. There cannot be factored. So what you're gonna do is use the completing the square on the part that cannot be factored, and then everything comes out fairly straightforward. So let me show you here. Okay, so first you break, I use the fraction calculator to break that thing apart. So then I have the first part, the answer comes out nicely. The second part, I had to do the completing the square, okay? And then let u equals to that very x plus 1, which gives you something like this, eventually, I guess. And once you get that, then for some reason, I wrote it in 2 chunks. Doesn't matter. The point is, this is where you get, and then you break this thing into 2 chunks. And one of the u plus 1, u squared, 1 over u squared plus 1 equals to the tangent situation, where, tangent inverse. And the other one is just a straightforward u substitution. The one on the far side, u over u squared plus 1, negative. So then by then you can plug in pull all the answer out appropriately. Right, is that, and then the final answer is, no, give me a second. I'm missing something here. Sorry, I made a mistake. What happened is that there is no tangent in this story, because when you plug in u equal to x minus 1, x plus 1 right here, you end up being, the top end up with just minus u. Okay, that's why my answer didn't have tangent in there, but it would have been nice if I had scratched it out earlier, right, when I noticed that. But apparently, you just, I neglected to do that, so I was confused just now. But now that I figured that out, you just have to integrate the minus u over u squared plus 1, which is a direct substitution, and come up with the answer right here, and that is correct. So that's good. Next, let's look at problem 215. Now, 215 is a very cute problem, and it also demonstrates a trick that you can pull. For 215, let's look at this. Okay, the problem says 1 over e to the power x over e to the 2x minus e to the x. And you're thinking, why does it say that? Because normally such a problem would have been presented as on this side. See, it's 1 over ex minus 1, right? What's with all the x's? Well, as it turned out, when I was staring at the x's, then I realized something. The x's, the extra e to the power x is there as a hint. So what you do is then the derivative on the bottom, and the top, ex dx, takes care of du, see? For example, like if you use u equal to e to the power x, then du equals to e to the x dx, and then everything comes out very nicely. See, it just becomes a basic fraction, 1 over u squared minus u, which the partial fraction calculator will break it up for you, and then everything, and all the rest of the answer is a piece of cake. So the answer end up being natural log of e to the x, which is just x, because natural log and e are inverse functions, and then plus natural log of some other stuff, and then you're home free. But that was a pretty nice problem, which shows that sometimes you might want to multiply e to the power x. That's another trick to fix the problem that otherwise looks basically impossible. So that's 215. Next, let's look at problem 219. Next, let's look at problem 219, where you integrate a bunch of e's. Now, e's are often easy to use do for integration and differentiation because of its neat property of the derivative of e is e itself. In this case, that also worked out pretty nicely. So you have e to the power t minus e to the power minus t in the denominator. What you're going to do is play some fractions, okay? That is, e to the minus t is just 1 over e to the power t. Then you multiply that thing out, and then on the third step, you let's see here. Then you flip it around, okay? Divide by the whole fraction and flip it around so the e to the 2t goes on top, and the rest of that stuff go on the bottom right here. That's a bit of a basic division algebra. Now, once you did that, then you notice that the fraction has e to the 2t on top, so it takes care of the the derivative of the bottom. Basically, is part of it becomes the top. So you take care of the du situation. See right here on the second page, and the next line. I mean, u equals to 2. If you set u equal to 2 to e to the power 2t, then du is still have e to the power 2t dt, which takes care of what's on top. So the integration then get turned into some kind of a perfect squared 1 over u minus 1 squared. And at that point, you don't even need to worry about partial fractions. What you do at that point is you do a second quick substitution where v is u minus 1. And then that the whole integral becomes, integral 1 over 2v squared, a quick power integral. So that gives you what it is in terms of u. And then don't forget to plug everything back in. Okay, v is u minus 1, plug that in here. And then u is e to the power 2t, plug it in here. And then you get the right answer. Now, next, let's look at problem 221. Next, let's look at problem 221, the integral of dx over 1 over 1 plus square root of x plus 1. You're thinking, well, how am I supposed to do that? That's not even a polynomial. You know, we're supposed to be doing this and doing partial fractions. Where's the partial fraction? Well, in this problem, here's a trick that I pulled. Well, just at random, really. So what I did is I let u equal to the entire denominator like this. So u equals to 1 plus square root of x plus 1, and then that would mean that square root of x plus 1 up here, okay, equals to u minus 1, all right? And then du will be then equal to all that stuff, 1/2, etc., okay? And then you think, wow, how are you going to get that to come out? Well, in this, normally you wouldn't, but in this problem, it happens to work out by luck, okay? So let's look at how my luck goes. Now, so next we have, so what happens is that du equal to all that stuff. So remember earlier I said that square root of x plus 1 is equal to u minus 1. So I plug that in here, okay? Put u back in there. So I get 2 times u minus 1 du equals to dx. You notice how neat that is, right? You don't have any square roots or anything ugly. So then you end up with a very simple integration, this thing right here, which can be easily integrated. You don't have to do any partial fractions or nothing. And it equals to whatever's over there. And then that can be quickly integrated to be 2u minus 2 natural log of u. And then you plug u back in. What was u again? U is that whole chain of stuff. 1 plus square root of x plus 1. So you plug in the u. And then the answer is, will fall right out like this. See this, and that answer is correct. Now, that problem shows you that integration is a lot like looking for something that you forgot where you put it. You might look here and there and everywhere, and just try random locations to look for, and then and once in a while you just luck out. It might take you a long time to look, but that doesn't mean the search itself, the getting the stuff is difficult. You just have to luck out and find the right path. So that so that's that. Next, let's look at problem number 227. Next, let's look at problem 227, which is we're going to refer that to earlier problem 215, where there was an extra e in there that ended up being very helpful. So we're going to take a page out of that book and do the same thing here. We're going to slap on some extra e's. Let's see, what did I do? Yes, so we'll multiply by e to the power x on top and on bottom. That way we can maintain the equality, okay, because we're not changing anything. And then once we get that, we will let u equal to e to the power x, which will quickly land us in a nice situation where it becomes a simple fraction, and we'll break it apart with a fraction calculator, and then take the natural log and substitute e back in there, and there comes our answer. So that's very nice. Next, let's look at problem 229. Yeah, look at that. That you have a square root of x plus cubic root of x. Like, how are we supposed to do that? Okay, that doesn't look anything like a fraction. I thought we were supposed to do fractions. Well, the book also provides a neat trick, which is let x equal to u to the power 6. And why would I want to do that? Because if you do that, everything will fall out. It's like pointing out what you lost is look in a very specific location. A weird hint that nevertheless works out. So let's look at that. Problem 229. If you let x equal to u to the power 6, and then u, of course, equal to x to the power 1/6, then dx equal to that. Okay, and when you plug everything in, you end up with a nice little fraction, which is what we're supposed to know how to do in this section. Okay, once you get the fraction, you break it up with a fraction calculator or by hand, and then you have once it's broken, then you readily can integrate each chunk of the broken thing. Okay, and then you plug in. What was u again? U was let me put it closer. Why is it not? Okay, my camera focused. So then you get everything back. U is x to the power 1/6. Plug it all back and fix everything up. So that's what you get, and that is correct. See, it's a neat trick. There's all these weird little neat tricks for different problems, and there's no guarantee that you're gonna find it. People just find it by trying different things. Kind of like I said, it's like looking for stuff in your house that you forgot where you put it. You just look everywhere basically until you find it. It might take a long time, but doesn't mean the job itself is hard. I mean, it's just a matter of luck, really. If it's in the first place you look, then you hit it right away. The last problem is problem 243. And you have to integrate cubic root of x minus 8 over x. It's like, what are you supposed to do with that? What happens is that, so after you beat around a little bit, and it's like, I have no idea how to do that. So then you get a hint. The hint is that you let u equal to the entire numerator. That's the cubic root of x minus 8. And then you figure out the the du and stuff, and that's, let's see, where do I have written that? Doesn't matter. The point is, then you get something about du. See, then you have the u processed out, then u cubed equal to x minus 8, etc. Then you have the dx equal to this bunch of things. This is similar to a previous problem where you let, I don't know how similar it is. Maybe it's not that similar. Doesn't matter. The point is, then you dx have a kind of a convenient bunch of stuff. And also x equal to u, and you also figure out that x equal to u cubed plus 8. All right, now with that, then you are quite equipped, okay? Because then you plug everything into the integral instead of a cubic root. Now you end up with something like that, much more manageable, being that we do know how to do, this is a fraction, right? And we do know how to do fractions, the rational function. So you break that up with the calculator, and it becomes that thing. The first two terms are pretty okay. The third thing is the hard one. Let's see. For some reason I wrote down x here. This is still u here. Okay. So we've gone back to u situation, and then let's see. Well, anyway, so that, I think, you have to do the completing a square trick, because that cannot be factored. Once you completed the square, then you do a second substitution where v is equal to u minus 1, and that becomes some situation that has the tangent inverse in it, because the tangent inverse does 1 over u squared plus plus a squared. So then you get everything to come out. So you have the first part, which is just the natural log of something, and the second part is the tangent inverse. And once you've done that, then you plug u back in, because v is some kind of u, right? V is u minus 1. Yes, you plug that in, and then u is the cubic root of x minus 8. So you plug that in, and yeah, and then that is the entire answer when you plug it all in. Look how long it is. It might be long, but it's right. And it's a couple more steps, or a couple more processes, and the answer looks long and intimidating, so you can show somebody that answer and freak them out. But in reality, it's not that much harder. Well, once you realize that you're supposed to, this is the hint, is what break the ice right apart, is that u equals the cubic root of x minus 8. And once you do that, yeah, so then the answer falls out. But you do have a big long answer that you probably never come up with some answer that long. But just because some answer is long doesn't mean it's hard. There's a difference. And with that, we marks the end of this section.